Okay, good morning. This is Weather and Climate, Geography 3500, Spring Semester 2021. I'm Dr. David A. Padgett. Today is February the 25th. So we are going to pick it up where we left off last time. And so where we left off last time was looking at the assignment 5 Hawaii lapse rate exercise. And so what I want to do today, need to share my screen. What we'll do today is just walk through the exercise and get you far enough along that you can complete the exercise yourself. But basically, at the heart of today's exercise is this fact or fun fact, or some people or most people probably do not realize that there is snow in Hawaii. And so given the location of Hawaii, which is just south of the Tropic of Cancer in the Pacific Ocean, one would not expect to find snow in Hawaii. However, when you read this article entitled Hawaii's Highest Peak Keeps Lone Snowplow Busy, you'll see that they meaning the Mauna Kea mountain, can receive as much as 14 feet of snow here in 1990. So you could never imagine snow in Hawaii. But Mauna Kea is almost 14,000 feet above sea level at its summit. And so what we're going to learn about through this exercise are the various dynamics of orographic climate controls. And so when we speak of orographic climate controls, and I will put that in the chat for everyone to see. Orographic. Orographic climate controls are ways that climate and weather, in fact, are influenced by mountains. And so there are several ways we'll learn about how mountains influence climate, including the one that we're going to talk about via this exercise. But while we're on the subject of orographic climate controls, let's go to the our vocabulary words and get into a discussion of some of the phenomena surrounding orographic climate controls. So we're going to talk about that. We have more. We'll talk about those, but I want to talk first about the phenomenon of altitudinal zonation. And so what happens with altitudinal zonation is, as you know, as we move farther away from the Earth's surface, that temperatures become cooler as gases expand and are less capable of holding heat. The subsequent effect is upon vegetation. And so here we have a cross section, presumably of the Andes mountain range. And so if you notice that the Andes mountain range, in this case, goes from sea level and up to over, well, really over 15,000 to 20,000 feet above mean sea level in some cases. And so near the near sea level, because much of the region around the Andes mountain range is in the tropics, we see, or in the tropical zone between the Tropic of Cancer and the Tropic of Capricorn. And so, those are where the sun's direct rays visit the earth throughout the year. We would expect for temperatures to be hot, tropical. And so near sea level, that zone, that altitudinal zonation zone, is called the Tierra Caliente. Of course, caliente translates as hot in Spanish. The next zone is the Tierra Templada. And as you notice here, we note that we see a different type of vegetation and different crops grown here. I'm gonna close this out. Maybe we have another image of altitudinal zonation. That here's another one of Mount Everest. And so you can see that this one's in meters. With Mount Everest, you can see how we go from rainforest near sea level, and as we move farther away from the Earth's surface, there's a subsequent impact upon the vegetation. And that is because as the atmosphere gets cooler and cooler and cooler as we move away from sea level, that influence, of course, drives what kinds of plants we see. And that is because plants have very specific tolerance ranges in terms of temperature and precipitation. And so this phenomena of altitudinal zonation is one type of orographic climate influence or climate control. But getting back to the exercise, and so that is the Hawaii Lapse Rates exercise. As I walk us through this exercise, I'm going to, of course, discuss some of the things or phenomena that we see associated with orographic climate controls, not only in Hawaii, but also obviously the Himalayas and the Andes mountain ranges, the Sierra Nevada mountain range in North America, and the Rocky Mountains, and so on and so forth. Okay, so we've read the attached article, and so we are going to discuss these various lapse rates. So the lapse rates are the rates at which temperatures change in the atmosphere as we move away from the Earth's surface. So the environmental lapse rate is the rate at which the atmosphere temperature changes as we move away from the Earth's surface. And we'll talk about that. That's the surrounding atmosphere. Then we have the dry adiabatic lapse rate, which is the rate at which a parcel of air or a pocket of air changes as it moves away from the Earth or as it sinks. And then the saturated adiabatic lapse rate is the rate at which a parcel of air changes temperature after condensation has taken place within that parcel of air. So those things will make a lot more sense as we move through the exercise. So the instructions at number 2 say to draw a schematic profile of Mauna Kea, preferably on graph paper, but you can just use line paper. And so I have a sheet of paper here. And so I'm going to draw a profile of Mauna Kea here. Maybe it might be better if I use a magic marker, just so that it shows up a little better than this pencil here. So what you should do is on your sheet of paper, just mark off I'm going to have to start over because artistic skills are lacking. So you're going to start off at sea level and then go at 1,000-foot increments away from the Earth's surface. So that's step one. Even though I was hoping that we would have done this prior to class, but so we're going to draw a schematic profile of Mauna Kea. So we're going to round it up to 14,000 feet. So on this sheet of paper, I've drawn on one side, that's the elevation. And then you're just going to draw as best you can. I know that this isn't an art class, but as best you can. Water, and then the profile of the mountain range, similar to the way it looked. So this is cross section of the mountain range. It says a draw an arrow somewhere indicating prevailing wind direction. So the wind direction is going to blow from the left-hand side of the mountain range to the right-hand side. So that's our prevailing wind direction. We have our elevations level. Now at 9,000 feet, notice it says from the article that the Keck lab is at 9,000 feet above mean sea level. So you should just make a marker there. Okay, so now we are ready to begin to examine the various properties of air masses as they move through the atmosphere. And so I know that the whole idea of thinking of air as having liquid properties is a bit abstract, but that's exactly what we're talking about here. Imagine air acting with liquid properties. I know it's a bit abstract physics, but just try to keep that in mind. Okay, so notice it says calculate the following. If a parcel of air at sea level at a temperature of 80 degrees Fahrenheit began to rise up the windward side of Mauna Kea, moved over the peak and then down the leeward side, what would its temperature be? So it says a parcel of air. So if we draw a parcel of air, you could represent it simply as a circle at the bottom of there at sea level, parcel of air at sea level. And then inside of it, you might want to draw like an 80, that represents 80 degrees Fahrenheit. So that is the first part of our work here. Next, we would want to draw in the ambient temperature. So we'll go back to our directions. Notice that the sea level ambient temperature is 78 degrees Fahrenheit. So that's the surrounding air. And so maybe somewhere over here near this 80. So right there, it's 78 degrees Fahrenheit. They're in proximity to the 80 degree Fahrenheit. So now we have our ambient temperature and our the partial of the temperature of the partial of air, excuse me. So now the scenario is if a partial of air at sea level temperature of 80 degrees Fahrenheit began to rise up the windward side of Mauna Kea, moved up over the peak and then down the leeward side, what would its temperature be? Okay, first at 3,000 feet on the windward side. So the windward side of the mountain is the side of the mountain that is facing the wind. This partial of air at 80 degrees is going to rise to 3,000 feet above sea level. So it goes from sea level up there to 3,000 feet. So the question is, what would its temperature be at 3,000 feet on the windward side if it cools at the dry adiabatic lapse rate of -5 degrees Fahrenheit? So it's going to become 5 degrees Fahrenheit cooler every 1,000 feet. Okay, so can anyone take a venture guess? What would the temperature be if it starts at 80 degrees Fahrenheit and cools to 5 degrees every 1,000 feet? What's its temperature going to be at 3,000 feet above sea level? Just anybody.
Please, what's the question again?
Yes, so if we have a partial of air that is at sea level at 80 degrees Fahrenheit, it's going to rise to 3,000 feet above sea level. Now, you might ask, well, how does a partial of air rise? Well, it's being pushed along by prevailing winds. So it's forced to rise over the top of this mountain. But right now, we just want to know how much does the temperature change from here to there? Okay, start at 0, up 3,000 feet above sea level. How much does the temperature change if it decreases in temperature at a rate of -5 degrees every 1,000 feet? What would its temperature be at 3,000 feet above sea level, given that rate of cooling?
Uh, 65.
Yes, 65 degrees Fahrenheit at 3,000 feet above sea level. Okay, so what do we know about 365 degrees Fahrenheit? We know that that is the dew point of this parcel of air. So this parcel of air reaches its dew point at 65 degrees Fahrenheit. Well, it's reached 65 degrees Fahrenheit, which means that now condensation is taking place within this parcel of air. But it's going to continue to rise up to 6,000 feet. But now, instead of cooling at 5 degrees every 1,000 feet, it's going to cool at 3 degrees every 1,000 feet. And you might ask, well, why is that? Why does the lapse rate change after condensation? Okay, so this is one of the laws of energy. I think it's the law of energy conservation. which means that basically the amount of energy can either be created nor destroyed, right? So if you think about air in its gaseous state, right? So air, otherwise, i.e., water vapor, which is a gas, molecules are moving very quickly. Now that gas becomes a liquid and the molecules slow down. Well, where did that energy go from here to here? Did it just disappear? No, that energy is released from that water as it moves from a gaseous state to a liquid state in the form of heat. And so that is called the latent heat of condensation. Let me just type that into the chat. You can look that up somewhere. It's called the latent. Latent also means hidden. Latent heat of condensation. So what happens is when condensation takes place, heat is released. And so that counters the cooling rate that occurs when a parcel of air moves away from the Earth's surface. Okay. And so you might have noticed, or if you watch the news, or even if you've been outside, but especially when it snows, if you've ever noticed, maybe not, that when it snows, it gets a little bit warm. It feels a little. Feels a little bit warmer, and you might think, well, this is maybe I'm imagining this. No, it's actually true. You know, that latent heat of condensation actually makes temperatures warmer when we start to see snow and rain. That latent heat of condensation now counters the rate of cooling in this parcel of air so that it no longer cools at 5 degrees Fahrenheit. Now it cools at a rate of 3 degrees Fahrenheit for every 1,000 feet. So at 6,000 feet, what would be the temperature of this parcel of air if it's cooling now at 3 degrees Fahrenheit? It's getting cooler by 3 degrees Fahrenheit every 1,000 feet. What's the temperature at 6,000 feet above sea level?
Would it be 74?
No, it's losing. It's cooling off, so it's getting cooler. So at 6,000 feet, it's 65 degrees Fahrenheit. At 3,000 feet, it's 65 degrees Fahrenheit. At 6,000 feet, what's this temperature going to be?
Would it be 50 56?
Yes, it'll be 56 degrees Fahrenheit. So now at 6,000 feet is 56 degrees Fahrenheit. What about at the Keck Observatory dormitories? The Keck dorms are at 9,000 feet above sea level. What's the temperature going to be there? It's still saturated. So what's the temperature going to be at 9,000 feet above sea level?
$47.
Okay, 47 degrees Fahrenheit. What about at the peak of Mauna Kea? What's the temperature going to be at the top of the mountain? Still cooling at that same rate.
What's the feet at that level?
Excuse me?
What's the feet?
Oh, the peak is at 14,000 feet. Remember, we rounded it up to 14,000 feet.
$32.
32 degrees Fahrenheit. Okay. Isn't that interesting? 32 degrees Fahrenheit. Now what's going to happen is the parcel of air is going to descend on down the leeward side of the mountain. As that parcel of air descends, it is now free of moisture because the moisture has precipitated out on the windward side of the mountain. So now we have this dry parcel of air that is going to descend down the leeward side of the mountain. And as it descends, it's not going to cool off. It's going to become influenced more greatly by the pull of gravity. The gases are going to compress and it's going to warm up. So as this parcel of air goes from the peak of Mauna Kea and gets to 8,000 feet on the leeward side, now it's going to increase in temperature 5 degrees Fahrenheit every 1,000 feet. So it starts at 32 degrees Fahrenheit. What's the temperature going to be at 8,000 feet above sea level on the leeward side? So it's going from 14,000 feet to 8,000 feet. So what? That's a 6,000 foot difference.
You said it's increased by 5 degrees.
Yes, 5 degrees Fahrenheit every 1,000 feet it descends. So it's going to descend 6,000 feet.
$62.
Yes, 62 degrees Fahrenheit. Okay, what is the temperature going to be on the leeward side at sea level? Now it's going to go from 62 degrees Fahrenheit at 8,000 feet, and it's going to descend 8,000 feet down to sea level. What's its temperature going to be at sea level?
102.
Yes, 102 degrees Fahrenheit. So what we have illustrated here in our schematic is something that is called the rain shadow effect. And so if we look at the rain shadow effect in Hawaii, you'll notice that here we have the northeast trade winds, and we'll talk about wind belts. So here's the prevailing wind direction. Here's Mauna Kea. Notice on the leeward side of Mauna Kea is rainforest, lush rainforest, trees. On the leeward side, it's desert. So I've never been to Hawaii, but from what I've told, you can actually go on a hike where you start off in this tropical side of Mauna Kea, and by the time you get over to the leeward side, you're in a completely different ecological and vegetation environment within a relatively short distance. You go from rainforest to desert. And so that is called the rain shadow effect. The world's deserts are found on the leeward side of mountain ranges. And so here is another schematic diagram of the rain shadow effect, where parcels of air reach their dew point on the windward side, moisture precipitates out, and then on the leeward side of the mountain range is where we find a much different environment as this dry air compresses, is warmer, and that has a significant influence upon the vegetation that's found on the leeward side of these mountain ranges. So that is what we call the rain shadow effect. Okay, let's move further into this. Okay, so you all are responsible for completing the rest of this is answering the rest of these questions. Okay, I'm going to give you some hints. So what you should do is take your schematic diagram here in order to answer the following questions. Okay, but I'm going to give you a few clues to help you along the way. So you should look over this presentation of Earth in the climate system, and it does, you know, there's various vocabulary words that are in here, including saturation and so on and so forth, and graphic description of these various lapse rates. Okay, so here's a slide. Here's how air becomes saturated. And so as I described, we have the moist adiabatic lapse rate and the dry adiabatic lapse rate. And so when we see condensation take place, one of the things that happens is the water vapor becomes visible to the human eye in the form of clouds and rain. And so this is a graphic sky diagram of the moist versus dry adiabatic lapse rate. So the change over from dry to moist here. Should take a look at that. Atmospheric stability. Okay, so we have stable conditions occur when a parcel of air is at the same temperature as the air surrounding it. Unstable conditions occur when the parcel of air is warmer than the air surrounding it. Okay, so I'm going to go back to our schematic diagram, okay, and back to the instructions, okay, to give you a little bit more information. So if you notice, the environmental lapse rate is 3.5 degrees Fahrenheit for every 1,000 feet. So if you remember, we started with a sea level ambient temperature of 78 degrees Fahrenheit. Probably put that. So if at sea level, okay, the temperature is 78 degrees Fahrenheit, and the air cools at a rate of 3.5 degrees every 1,000 feet. So remember, this is the surrounding air. I know this is kind of difficult to grasp and visualize, but just try to think outside the box. So if the surrounding air cools at a rate of 3.5 degrees every 1,000 feet, what is the temperature of the surrounding air at 3,000 feet? So the parcel of air is 65 degrees Fahrenheit. The surrounding air is what temperature? So what you imagine, you're on a balloon and you take off. It's 78 degrees Fahrenheit at sea level. The air gets colder, 3.5 degrees Fahrenheit. Your balloon rises to 3,000 feet above sea level. What's the temperature going to be? If it cools off 3.5 degrees Fahrenheit every 1,000 feet you rise in that balloon.
This is 67.5.
So at 3,000 feet above mean sea level, the ambient temperature is going to be 67.5 degrees Fahrenheit. Okay, that's your clue. Now when we talk about stability or instability, we're speaking about those characteristics or properties being associated with the parcel of air. Is the parcel of air stable or unstable? So here's what's going to happen. If a parcel of air is warmer than the air surrounding it, okay, is it going to be less dense or more dense than the surrounding air if it's warmer? Less dense or more dense? Is warmer air less or more dense than cooler air?
Cooler air is denser.
Yes. So if a parcel of air is warmer than the air surrounding it, it's going to be
denser.
Excuse me?
It's going to be less dense.
Yeah, it's going to be less dense, which means it's going to those are unstable conditions. Why are those unstable conditions? Because if that parcel of air is warmer than the air surrounding it, then it's going to have a propensity to rise. Okay, so parcels of air can rise even without being pushed along by the wind. This is called atmospheric lifting. And so in your list of vocabulary words for today, I think we have mentioned the various types of lifting. So there's frontal lifting, there's orographic lifting, and there's convectional lifting. So we're talking now about orographic lifting. That's when a parcel of air is forced over top of a mountain range, is forced higher into the atmosphere as it goes over a mountain range. That's orographic lifting. There's also frontal lifting. Now, we talked about frontal lifting yesterday, when warmer air rises up over top of cooler air at frontal boundaries, which results usually in precipitation. Then there's convectional lifting. Convectional lifting is most closely associated regionally with Florida. So Florida gets a lot of precipitation, a lot of thunderstorms. Convectional lifting is when air is warmed at the Earth's surface, becomes less dense and rises. Eventually it cools to its dew point, then there are clouds and precipitation, okay? So if we are in a situation, or if we have observed a situation where air is less dense than the air surrounding it and begins to rise, those conditions are unstable because there's going to be a change. If that parcel of air is likely to move, there's going to be a change, which means that something's going to happen. Okay, so there might be rain or some kind of change. Now, and in those cases, and this makes perfect sense, the types of clouds that we would expect to see under unstable conditions are those cumulus clouds and cumulonimbus clouds. So if you can imagine, as this parcel of air is rising, and clouds are forming, they're very puffy because the air is rising. Now, conversely, if conditions are stable, if we have stable conditions, then the parcel of air is resisting. Even if a parcel of air is cooler than the air surrounding it, even if it's being pushed by prevailing winds, it's not going to rise very quickly. And so under those conditions, we have those stratus, the flat clouds form along those pressure boundaries, okay? And so cumulus clouds are associated with unstable conditions, whereas stratus clouds are associated with stable conditions. So let's look at our cloud nomenclature. Notice that clouds are defined based upon their shape and their height. So when we start off below 6,000 feet, those are, you have just cumulus, stratus, sometimes there's a mixture, stratocumulus, and so on and so forth. If those clouds produce rain, then they're called nimbostratus clouds, if they're a stratus cloud. If a cumulus cloud produces rain, it's called a cumulonimbus cloud, otherwise known as a thunder cloud. These are the types of clouds that are associated with thunderstorms and tornadoes and severe weather. As we get higher in the atmosphere, notice when we get from 6,000 to 20,000 feet above sea level, now we have alto cumulus and alto stratus clouds. The alto represents the height. Then when we get very high, we have cirro cumulus and cirro stratus clouds, and so on and so forth. So the cloud types are not only are associated with their height, but they also form under different conditions of stability in the atmosphere. So these cumulus clouds, unstable conditions; stratus clouds, stable conditions. So that is the hint that I'm going to give you in answering some of these questions. At what elevation would you first expect to see clouds form? Explain your answer. Would the clouds form under stable, unstable, or neutral atmospheric conditions? Explain your answer. I think I've given you enough information to answer that question. Under such conditions, what types of clouds would you expect to see? Explain your answer. D, at the peak of Mauna Kea, what form of precipitation would you expect to see fall from the clouds? Now, remember, we talked about different forms of precipitation earlier. We talked about rain, liquid precipitation, freezing rain, solid form. We also have sleet, frozen precipitation that falls as a liquid, freezes upon hitting the ground. Then we had hail. Now, hail is associated with thunderstorms and violent weather like tornadoes. Okay, so that's, and then finally, we have snow, which is when deposition occurs, when we have water vapor go from a vapor to a solid without ever being a liquid. When that happens, crystals form that we call snowflakes. That's what snowflakes are. They're crystals that are created during the deposition process. Gas going from a gas to a solid without ever becoming a liquid, without ever going through the liquid phase. Your last question is to discuss the impacts that mountain ranges have upon climate. Think you have enough material to answer that question pretty easily. So what you should do is, again, you should either scan or photograph your final schematic, upload this along with the answers to these questions before the Dropbox deadline next Tuesday. So I've given you a few hints. We'll talk about the answers next week when the assignment is due. So does anyone have any questions at this time? I don't think there's anything else we need to cover. Let me go and just make absolutely sure that we have covered everything here. The layers of the atmosphere, composition, the various types of lifting, the lapse rate, stable conditions, and cloud formation processes. Yes, so all of that is incorporated within, all those concepts are incorporated within this exercise. And so you have a variety of resources here to assist you in answering the question and questions associated with this assignment. And so I want you to attempt to answer those questions as best as you can. I've done most of the math for you today. So I don't think there's any math left. It's just looking at the effect of these various atmospheric conditions upon the Earth and upon the atmosphere itself. So if you have any questions about the exercise, let me know. Please let me know if you have any questions so that we can have an interesting discussion next week. Oh, almost forgot. I almost forgot. Let's do today's weather map. So here's a daily weather map. Let's take a look at it. AMS data stream page. Scroll down to isobars, fronts, radar, and data. And so here we have today's weather map. So again, what you are going to be responsible for on the midterm is I'm going to show you a map like this one for that day. And I'm going to ask you certain questions about specific cities in terms of what you would expect to see. So I think today we're probably at the point where we can do a little bit of practice perhaps with this. Okay, so let's see. Theodora.
Yes, Dr. Padgett.
Can you find, say, Atlanta, Georgia on this map? Okay, here's Nashville.
So
That's,
it's below.
yeah, this is Atlanta right here.
Okay.
What type of weather front is influencing Atlanta right now, today?
I'm not sure.
Okay, Garrett, you want to give it a shot?
Guess
yeah,
the hop down or something.
Excuse me? Yeah, what kind of weather front is influencing Atlanta, Georgia right now?
Weather front. I'm not sure.
Okay, here's Atlanta. See Atlanta right here?
Yeah.
Okay, do you see the blue line symbol?
Yeah.
What is that? Okay, what kind of front is that? Okay, I'll make it a little easier. Is it a cold front or a warm front?
Oh, it's a warm.
No, it's a cold front. Remember your weather symbols, those teeth marks, the blue teeth marks, that's a cold front. Let's look at, can either of you find the state of Nebraska on this map?
Yeah.
Is Nebraska right now under the influence of high pressure or low pressure?
Guess high.
Yes, the big blue H there, high pressure there. Okay, approximately what is the barometric pressure? That's probably Lincoln, Nebraska. What is the barometric pressure at the weather station at Lincoln, Nebraska right now in millibars? Okay, here's Lincoln, Nebraska.
Is it the 319?
Is it 319? Okay, let's look at the closest isobar. Here's the closest isobar. Here, you kind of can't even read. Okay, the closest isobar. Here's an isobar. That's 1,000. Well, actually, there's little piece of an isobar here. Can you see that? That says 1,032 millibars, okay? So given what I've just told you, what is the barometric pressure at Lincoln, Nebraska right now?
Like 1032.
No, it's so this. What is this? It says 319 there. How would we read that in millibars? Okay, so you remember we truncate the leading 1 and 0 because we pretty much assume that barometric pressure is going to be at least 1,000 millibars. We don't see, when we get to 900 millibars, and like that's when we have hurricanes and really low pressure systems. But for the most part, under normal conditions, barometric pressure is going to be at least about 1,000 millibars. So in order to simplify or generalize the map, the cartographers and or meteorologists truncate that value by dropping off the leading 1 and 0. Okay, so again, now that you know that, what is the barometric pressure at Lincoln, Nebraska right now in millibars?
Would it be 32?
Excuse me?
32.
No, actually, it's 1,031.9. Okay, so you drop off the leading 1 and 0, and after the first two figures, you drop in a decimal point. So Lincoln, Nebraska, it's 1,031.9. And I believe this is Des Moines, Iowa, it's 1,029.7. And where is the one we can easily see? That was the easiest one to see. At Minneapolis, Minnesota, it's 1,028. Okay, let's go back to Lincoln, Nebraska, since that's easy to see. What is the current temperature at Lincoln, Nebraska, based upon this weather map in degrees Fahrenheit? Okay, you've got two choices. It's either 26 degrees or 22 degrees. Which one is it?
I'll say 26.
Yes, the upper left-hand value is the current temperature. What's that 22 degrees Fahrenheit? What's that? What temperature is that?
The lower temperature.
No, that's the dew point temperature. Okay, what is a dew point temperature? What happens when air reaches its dew point? What happens? I mean, what is the definition of the dew point temperature?
Does that mean that the temperature at which air will cool? The temperature at which air will cool. Air cools.
Okay, and then what happens?
So your question was, what will happen? What happens at dew point temperature?
Exactly, what happens in the atmosphere?
There's moisture.
Yeah, what's that called? What's that process called when a gas turns into a liquid?
Gas to liquid.
Okay, it starts with the C.
Condensation.
Yes, condensation. The dew point temperature is the temperature at which condensation takes place. So if you were to read this map and you notice that you have a ambient temperature of 26 degrees Fahrenheit and the dew point temperature is 22 degrees Fahrenheit, those two numbers are close together, which means that there's a possibility that you might see precipitation. What's the cloud cover percentage at Lincoln, Nebraska right now? What percent of the sky is covered by clouds based upon this weather map? Is it 10%? Is it 50%?
I think all of it.
Excuse me?
Like almost 1%.
Yes, what percent cloud cover is being experienced at Lincoln, Nebraska right now?
100.
Yes, 100%. As you can see, that point symbol is completely dark. What about at, you see one that's easy to see, that one's hard. Okay, Indianapolis, Indiana. What's the cloud cover percentage at Indianapolis, Indiana?
Like 70.
Yeah, 75%. Notice that circle is filled in 3/4 of the way. Let's see. What about Jacksonville, Florida here? What's the cloud cover percentage there?
25. 25.
25%. So now we're getting that. So I'm going to save this map for you to practice with. And so just remember that on the midterm exam, I'm going to show you a map like this one, and you are going to have to answer questions exactly like that about a given city. Let's see. I might ask you a question. Let's see, that's probably,
I have a question.
yes.
So you see the red line with the half circles on there.
Yes.
What does it represent?
Yeah, that's a warm front.
Okay.
Yeah, so in your materials, I believe at the, let's see, is it week 4? Yeah, week 4 here, you do have weather map symbols. And so, here are all the weather map symbols: cold front, warm front, occluded front, stationary front. So you, sky coverage, wind direction, so on and so forth. So, and you also, weather station location, temperature, wind direction. I'll ask you about that. Percent sky covered by clouds, so on and so forth. So familiarize yourself with these map symbols because you will definitely be asked about them. Okay, so again, the Hawaii Lapse Rates exercise is due on Tuesday. And also the second article review is due on Tuesday. I think just to wrap things up today, I think Theodora says she's prepared to do her hometown city weather and climate presentation. And well, I guess both of you can do your hometown city weather and climate presentations. We'll let Theodora go first. So I'm going to stop my share. And so Theodora, are you ready to do your presentation? And then Garrett, you'll follow up.
Yes, please. Let me share my screen. Can you see my screen?
Yes.
Okay. Let me make it. Okay. Good morning, everyone. My name is Theodora, and today I'm going to give you a 5-day weather forecast for last week. And I'm reporting from Memphis for this class, which is Weather and Climate Geography 3500, and the instructor is Dr. David Padgett. So this is just a little bit of information about the weather, the general weather and climate in Memphis, Tennessee. The average temperature per year is 62.2 degrees Fahrenheit. The annual high temperature is 72 degrees Fahrenheit. The annual low temperature is 54 degrees Fahrenheit. The coldest, hold on one second. The coldest month is December with an average rainfall of 5.8 inches. The driest month is August with average rainfall of 3 inches. The hottest month is July with average temperature of 90.9 degrees Fahrenheit. The number of sunny days per year is 218 days out of 365 days. The average annual precipitation is 53.68 inches. The average annual snowfall is 3 inches, and the total rainfall is 52.1 inches. Okay, so these maps show the average annual rainfall in Memphis and the average annual snowfall in Memphis. So if we look at this map on the left, we see that Memphis right here has an average rainfall of, I'll say 54. As per this map, it shows it has 54 inches, and it's comparing it to the US. The US in total has an average rainfall of 36.5 inches of rainfall. And for the snowfall in Memphis, if we look at this map right here, we compare it to this, I'll say it shows here that it has about 3.2 inches of snowfall. And comparing it to the annual snowfall in US is about 25 inches, which is like, there's a very big gap. So I decided to do my weather forecast. Sorry, let me pause it. So my weather forecast, the dates range from the 18th of February through the 22nd of February. And so on the first day, I used a particular time for all my weather forecasts from 12 p.m. to 6 p.m. And the time, the highest temperature during that time was 28 degrees Fahrenheit. The lower temperature was 27 degrees Fahrenheit. And I'll describe the clouds as the clouds was an overcast, and humidity was 74%, and then the precipitation that day was 0.36 inches. So for the second day, which is 19th February 2020, the highest temperature during that day was 28 degrees Fahrenheit. The lower temperature was 25 degrees Fahrenheit. And the time I measured all the time is the same, so 12 p.m. to 6 p.m. And the day was sunny, was a sunny day with humidity of 60%. And there was no precipitation that day. So I decided to rather put the atmospheric pressure here, which was 30.44 inches Hg. So for 20th February 2020, the higher temperature was 43 degrees Fahrenheit, so that it was beginning to warm up a bit. The lower temperature was 37 degrees Fahrenheit. The skies were clear. Humidity was 47%, and then the atmospheric pressure was 30.37 inches Hg. Again, there was no precipitation on that day. For the 21st of February 2020, the higher temperature was 55 degrees Fahrenheit. The lower temperature was 52 degrees Fahrenheit, and it was mostly cloudy that day. The humidity was 53%, and the atmospheric pressure was 30.11 inches Hg. This is the last day, and for this day, the sorry. Okay. Yes. So for this day, the higher temperature was 52 degrees Fahrenheit. The lower temperature was 39 degrees Fahrenheit. It was sunny that day, and the humidity was 64%, and atmospheric pressure was 30.18 inches Hg. So this is a map, a graph just comparing the temperature, the high temperatures of that day, the 5 days. We can see that the higher temperatures were recorded at noon, and it generally shifted to higher, warmer temperatures throughout the 5 days. And so this just a graph showing the precipitation in inches, and the only day that there was precipitation was the first day. It had 0.36 inches, and the remaining days had no precipitation. For humidity, we can see that there was a decrease then an increase. For the 5 days, there was a decline and there was a rise, basically. And for the atmospheric pressure, it was kind of constant throughout the 5 days. It was just minute changes in air pressure that was recorded. So there was snowfall, sleet, and ice of about 6 inches from Sunday, 14th February to Wednesday, 17th February, some days before this data was collected. And as a result, it's because Memphis doesn't really have snowfall we don't have this much snowfall on the regular. The average snowfall is 3 inches, but this time was more than expected. So, and Memphis doesn't really have the equipment to combat snowfall like that. So it caused damages to water and electricity supply. Some water pipes froze, burst, and leaked. And the Memphis International Airport was closed from Tuesday, 19th February to Saturday, 21st February, because of the water and electricity supply. And also, the ice on the ground made it dangerous for planes to take off and land, and flights were cancelled. My flights were cancelled, a lot of my flights. So I can really relate to this problem. And I have a video. I have a video. Can you see my screen still?
Yes. Yeah, Theodore, that's very good. I wish we had more time, but the class is
Okay.
about to end. But
Okay.
for those of you watching this recording, this is pretty much what I would expect for you to do. Thank you very much, Theodora. Garrett, we'll get to you next time. Again, please, if you have questions about this week's assignment, let me know, and be sure to do the reading because your midterm exam is rapidly approaching. So I will let you know when that's going to be. Enjoy the rest of your day.
Thank you and bye.